Right now, a machine floating more than 1 million miles from Earth is quietly rewriting what we thought we knew about the universe. For decades, scientists believed the cosmos was vast but ultimately measurable, about 14 billion light-years in every direction. Then the James Webb Space Telescope turned its mirrors toward what looked like empty darkness, and that certainty collapsed. Webb revealed galaxies forming just a few 100 million years after the Big Bang, black holes growing faster than theory allows, and structures appearing far earlier than expected. But the most unsettling discovery isn't how far Webb can see. It's what these findings imply about the true scale of reality, and how much of the universe may lie forever beyond our reach. If you're ready, hit that like button and let's begin. To understand what the James Webb Space Telescope is truly revealing, we first have to abandon a familiar idea, the idea that space is something we simply look across. In the universe, distance is not just distance, it is time. Light travels at a constant speed, about 300,000 kilometers per second. It is the fastest thing that exists, fast enough to circle Earth more than 7 times in a single second, and yet, even at that speed, distance immediately becomes delay. The moment light leaves an object, the clock starts. When you look across a room, you're seeing the past by a few billionths of a second, a delay so small your brain ignores it. When you look at a distant building, the delay stretches into millionths of a second, still too small to notice, still irrelevant to everyday life. But then the scales begin to change. When you look at the moon, you see it 2 seconds in the past. If the sun were to vanish this instant, its light would continue to arrive for 8 more minutes. From there, the delays grow beyond anything human intuition evolved to handle. The nearest star beyond our sun appears to us as it was more than 4 years ago. The centre of the Milky Way arrives 26,000 years late. When we observe the Andromeda Galaxy, we are seeing light that left its stars roughly 2.5 million years in the past, long before recorded history, long before cities, long before language. The night sky is not a live display of reality. It is a record. Every point of light carries a timestamp. Every photon is a messenger from a different moment in cosmic history. The farther that photon has travelled, the older the information it brings. But the universe does not preserve these messages unchanged. As the universe expands, space itself stretches. Not galaxies flying outward through space, but space expanding between them, quietly and continuously. And when space stretches, it stretches the light travelling through it. Wavelengths grow longer. Energetic blue and ultraviolet light shifts toward red, then slips into infrared. This effect is known as redshift, and it is not simply a change in colour. It is a physical record of how much the universe has expanded since the light began its journey. Redshift acts like a cosmic clock. The more stretched the light, the longer it has been travelling, and the earlier in the universe's history it was emitted. Distance and time become inseparable. To look farther away is to look deeper into the past. For decades, astronomers relied on telescopes designed primarily for visible light. The narrow band of the spectrum human eyes evolved to detect. Instruments like Hubble transformed our understanding of nearby galaxies, nebulae, and star-forming regions. They revealed motion, structure, and extraordinary detail. But as scientists pushed their observations farther back in time, the universe began to thin out. Not because it wasn't there, but because its light had changed. As light from the earliest galaxies travelled across expanding space, it was stretched beyond visible wavelengths. By the time it reached Earth, much of it no longer fell within the range those telescopes were designed to observe. Large regions of the early universe became difficult to read. The darkness was not empty. It was unreadable. The James Webb Space Telescope was built to read what earlier instruments could not. Webb is optimized for infrared light from the start. Its mirror spans more than 6 meters and is coated with a microscopically thin layer of gold, chosen for its ability to reflect infrared wavelengths with extraordinary efficiency. It does not orbit Earth. It operates nearly 1 million miles away at a stable gravitational point where it can remain steady and undisturbed. That distance is essential. To detect faint infrared signals, Webb must remain extremely cold. Infrared light is closely tied to heat, and a warm telescope would glow in the same wavelengths it is trying to observe. It would drown out the universe's faintest signals. Webb had to become quiet enough to listen. A massive sunshield blocks heat and light from the sun, Earth, and Moon. On its shadowed side, the telescope cools to temperatures where ancient photons can stand out against the darkness. Only then can Webb detect light that has been travelling for billions of years. When Webb stares into a region of sky that appears completely black to our eyes, it is not searching for nothing. It is waiting. Waiting for photons that began their journey when the universe was young, photons stretched almost to invisibility by the expansion of space itself. Those photons do not arrive in floods, they arrive slowly, sometimes one at a time. Webb may stare at the same patch of sky for many hours, even days, patiently collecting light that crossed nearly the entire observable universe. And what it finds there is not a quiet beginning. It finds activity. Galaxies appear where none were expected. Systems already forming stars. Structures already assembling. The early universe does not look tentative or fragile. It looks busy. There is something deeply humbling about this process. Webb does not capture images in the ordinary sense. Each image is a mosaic built from ancient travel, every photon in the frame having left its source long before Earth existed, long before the sun ignited, long before the Milky Way took its present shape. Every chapter of human history unfolded while that light was already on its way. By the time Webb detects it, we are not witnessing events happening now. We are witnessing moments that happened once, long ago, preserved in transit. They cannot be revisited, they cannot be updated. This is why astronomers say James Webb does not simply look far away. It looks backward through time. Distance becomes a timeline. Nearby objects show the universe closer to the present. Distant objects reveal earlier and earlier stages of cosmic history, layered behind one another. Yet even Webb's extraordinary vision has a limit. No telescope can see beyond a boundary set by physics itself. That boundary is defined by how far light has been able to travel since the universe began. It is known as the observable universe. It is not an edge of space. It is an edge of information. Beyond that boundary, space continues. Galaxies continue. Stars form and die. Black holes merge. Entire cosmic histories unfold forever beyond our reach, not because of technological limits, but because space itself is expanding in a way that prevents their light from ever reaching us. James Webb has not revealed the edge of everything. It has revealed how much of reality lies beyond what we can ever observe. And as Webb pushes closer to that boundary, detecting galaxies earlier, brighter, and more numerous than expected, a deeper realization begins to take shape. If the universe is already this rich at the limits of our vision, then the true scale of everything that exists must be far greater than anything we once imagined. For much of modern cosmology, the early universe was imagined as restrained. Not empty, but quiet. After the Big Bang, space expanded, temperatures dropped, and matter spread out almost evenly in every direction, leaving only small irregularities behind for gravity to work on. In this picture, gravity was expected to be patient. Gas needed time to cool. Dark matter halos needed time to grow large enough to trap ordinary matter. Stars required millions of years to form. Galaxies, when they finally appeared, were expected to be small and faint, fragile systems that would take hundreds of millions of years to mature into anything substantial. That expectation shaped decades of theory. So when the James Webb Space Telescope began observing the early universe, astronomers did not expect abundance, they expected scarcity. A handful of primitive galaxies scattered through a mostly dark cosmos, systems barely holding together, a universe still laying its foundations. Instead, Webb found crowds. Bright galaxies appeared again and again in eras that should have been nearly empty. These were not dim sparks clinging to existence. They were already active, already structured, already forming stars at intense rates. The surprise was not a single unusual object. It was the pattern. There were too many of them. Within the universe's first 500 million years, Webb detected galaxies producing enormous amounts of light. Some contained hundreds of millions, even billions, of solar masses worth of stars. According to long-standing models, assembling that much material should have taken far longer than the universe had available. Gravity is powerful, but it is not fast. Gas does not collapse instantly. It must lose energy and cool. Dark matter halos must grow through mergers and accretion. Stars must form, burn through their fuel, and eventually die. Each step imposes a timescale that cannot simply be skipped. And yet the galaxies were already there. What made this even more unsettling was not just their brightness or mass, but their chemical maturity. Webb detected signatures of elements like carbon, oxygen and nitrogen in some of these young galaxies. These elements were not created in the Big Bang. They were forged inside stars, and stars release them only when they die. Their presence meant something unavoidable. At least one earlier generation of stars must have already formed, lived and ended their lives, all within the universe's first few 100 million years. The cosmic clock was being pushed backward. To understand why this troubled astronomers so deeply, it helps to think in familiar terms. Building a galaxy is not a single step. It is a sequence. You cannot raise skyscrapers before roads exist. You cannot pour concrete before steel is made. Each stage depends on the one before it. The early universe was supposed to be laying foundations. Webb found structures already standing. This growing mismatch between prediction and observation became known as the too much light, too early problem. When astronomers calculated how much total light galaxies should produce during the universe's first billion years, their estimates fell short. Sometimes by factors of 2, 5, or more. That is not a rounding error. It is a signal. Scientists responded the way they always do. They questioned the measurements. They rechecked the instruments. They examined whether dust could be making galaxies appear brighter than they really were, whether gravitational lensing was magnifying distant systems, or whether assumptions about stellar populations were inflating mass estimates. Again and again the conclusion held. The early universe was not dim. It was luminous. Some of the galaxies Webb detected were so massive that researchers briefly referred to them as universe breakers, objects whose existence seemed to strain the limits of cosmology itself, because according to standard models, galaxies of that size should not exist at such early times. At first, there was hope that the masses were overestimated. Perhaps the light was not coming from stars alone. Perhaps actively feeding black holes were contributing extra brightness, making galaxies appear larger than they really were. Further analysis showed this helped, but only partially. Yes, some early galaxies host powerful black holes, and accounting for their contribution reduced the most extreme cases. But even after those corrections, the early universe still contained roughly twice as many massive galaxies as theory predicted. The tension eased. It did not disappear. Webb repeated these observations in different regions of the sky, using different instruments and wavelengths. Each time the same pattern emerged. The early universe was crowded. Star formation was efficient. Structure appeared rapidly. This forced astronomers to reconsider a basic assumption. How efficiently could the universe turn gas into stars? In the modern universe, star formation is surprisingly inefficient. Most gas inside galaxies never become stars. It is heated, stirred by turbulence, blown away by radiation, or disrupted by stellar winds, leaving only a small fraction to collapse into new suns. Early galaxies appear to have operated under different conditions. One possibility is density. The early universe was smaller, matter was packed more tightly together, and gas clouds collided more often. Another possibility is composition. The first generations of stars formed from nearly pure hydrogen and helium, without heavier elements to complicate cooling. Mergers likely played a role as well. In the early universe, galaxies were closer together. Collisions were common, and when galaxies merge, gas is driven inward and compressed to extreme densities, igniting intense bursts of star formation. Each of these ideas explains part of the picture. None resolves it completely. At the centres of many of these early galaxies lies another mystery. Webb has detected supermassive black holes already in place when the universe was less than 500 million years old. Some weigh millions or even billions of times the mass of the Sun. According to conventional models, that should not be possible. Black holes form from collapsing stars, producing objects only tens of solar masses in size. While they can grow by consuming surrounding matter, that growth is limited by the energy released as material falls in. Yet Webb keeps finding them. This has forced astronomers to consider possibilities once thought extreme. Direct collapse of massive gas clouds, early stars far more massive than those today, rapid mergers in a dense young universe. None of these ideas has been confirmed. None can yet be ruled out. What makes this era so important is that these early galaxies shaped everything that followed. Their radiation transformed the universe. Their supernovae seeded space with heavy elements. Their gravity sculpted the first large-scale structures. If they formed earlier and faster than expected, then the entire timeline of cosmic evolution shifts. And as Webb continues to look deeper into time, the pattern becomes harder to ignore. The universe did not wait. It assembled stars, galaxies, and black holes at a pace that challenges our equations, revealing that the early cosmos was not a fragile beginning. It was a surge. For much of the 20th century, astronomers believed they had reached a reasonable answer to one of the largest questions imaginable. How many galaxies exist in the universe? The method was simple in principle, even if difficult in practice. Point a powerful telescope at a tiny, seemingly empty patch of sky, count every galaxy you can detect, and then scale that number up to represent the entire observable universe. When the Hubble Space Telescope performed its deepest observations, the result was astonishing. In a region of sky no larger than a grain of sand held at arm's length, Hubble revealed nearly 10,000 galaxies. At the time, the image felt overwhelming. From it, astronomers estimated that the universe contained a few 100 billion galaxies. The number was almost impossible to comprehend, and for years it stood. Then the James Webb Space Telescope looked at the same darkness. Where earlier images showed gaps, Webb saw structure. Where black space once separated distant smudges, Webb detected faint infrared glows, layers of galaxies stacked behind one another, hidden not by distance alone, but by wavelength. This was not a failure of earlier telescopes. It was a limit of vision. As the universe expands, light from distant galaxies stretches into longer wavelengths. By the time that light reaches Earth, much of it no longer exists in the visible range those telescopes were designed to observe. The galaxies were always there. Their light had simply drifted out of reach. Webb was built to follow it. In one of its most ambitious deep-field observations, Webb focused on a region of sky only slightly larger than 3 full moons placed side by side. For hundreds of hours, it collected thousands of individual exposures, patiently gathering faint infrared signals that had been travelling for billions of years. When those images were combined, the result was staggering. Nearly 800,000 distinct galaxies filled the frame. 800,000 galaxies in a patch of sky most people would describe as empty. To appreciate the scale of that result, imagine printing the famous Hubble Ultra Deep Field on a single sheet of paper. To display Webb's image at the same level of detail, the print would need to be more than 13 feet tall and 13 feet wide. A wall-size portrait of cosmic history. And every point of light in that image is not a star. It is a galaxy. Each of those galaxies contains millions, billions, sometimes trillions of stars. Many host planetary systems. Many are rich in dust and heavy elements forged by generations of stellar birth and death. The universe is not sparsely populated with isolated islands drifting through darkness. It is densely packed. What makes this discovery even more powerful is that Webb did not merely count galaxies, it measured them. For each one, astronomers can estimate distance, mass, star formation rate, and approximate age. Taken together, these measurements allow scientists to reconstruct how galaxies evolved across nearly the entire lifetime of the universe. And when they did that, a deeper pattern emerged. Galaxies are not scattered randomly through space. They cluster, they align, they trace invisible pathways across enormous distances. On the largest scales, the universe resembles a vast cosmic web, long filaments of matter stretching tens and hundreds of millions of light years, intersecting at dense nodes where galaxy clusters form, and separated by vast regions where almost nothing exists. This structure had been predicted for decades. Webb revealed it with clarity. Many of the galaxies Webb detected were hidden behind dust that blocks visible light but allows infrared wavelengths to pass through. Entire populations of dusty star-forming galaxies emerged for the first time, filling gaps where earlier surveys saw emptiness and completing patterns that once appeared broken. This matters because the distribution of galaxies is not decoration. It is a record. After the Big Bang, matter was spread almost evenly through space, with tiny variations in density imprinted during the universe's earliest moments. Regions that were slightly denser exerted slightly stronger gravity. Over time, matter flowed toward those regions, amplifying the differences. Gravity carves space into filaments and nodes, draining matter from surrounding regions and leaving behind enormous voids. A useful analogy is rainfall over uneven terrain. Water flows into valleys, carving channels and rivers, while higher ground is left dry. Over time, a structured landscape emerges. The universe evolved in much the same way, except the flowing substance was matter itself. Webb's observations show that this process began early. Filaments tens of millions of light-years long already existed when the universe was only a few billion years old. Some structures were so large and so organized that they challenged expectations about how quickly matter could arrange itself. One striking example is a structure astronomers call the cosmic vine, a chain of more than 20 closely packed galaxies stretching over 13 million light-years. These galaxies existed when the universe was still young, yet the structure rivals much older formations in scale. What makes this structure especially intriguing is its state. Several of its largest galaxies have already stopped forming stars, having exhausted or lost the gas needed to create new ones. This is unusual so early in cosmic history. The implication is subtle. Environment matters. Galaxies in dense regions evolve differently than isolated ones. Interactions and mergers accelerate their life cycles. Growth happens quickly. Fuel is consumed rapidly. And this pattern is not rare. Using Webb data, astronomers assembled the deepest catalogue of galaxy groups ever produced. More than 1,600 groups and protoclusters spanning from roughly 12 billion years ago to just a few billion years ago. These groups represent the building blocks of today's massive galaxy clusters. By comparing groups at different distances, scientists can watch structure formation unfold across time. Early groups appear chaotic. Star formation is intense. later groups show increasing order, smoother shapes, and slower growth as gravity takes control. This continuous view across billions of years was not possible before Webb. Yet for all this density and organisation, the universe is also defined by emptiness. Between the filaments of the cosmic web lie vast voids, regions tens to hundreds of millions of light-years across that contain very few galaxies. These voids are not small gaps. They are the largest structures in the universe by volume. If you could stand at the centre of one and look in any direction, you would see darkness stretching for tens of millions of light-years before encountering the nearest galaxy. Entire regions of space fail to gather matter simply because gravity pulled that matter elsewhere. Webb's deep field images capture this contrast vividly. Dense clusters of galaxies appear alongside yawning black regions containing almost nothing at all. The universe is crowded and empty at the same time, which brings us back to the numbers. If Webb's deep fields are representative, and observations in different directions suggest they are, then the total number of galaxies in the observable universe may not be hundreds of billions. It may be trillions. For every galaxy we once believed existed, there may be many more hidden beyond the limits of earlier surveys. More galaxies mean more stars. More stars mean more planets. And suddenly, the universe becomes not just larger in size, but richer in possibility. Yet even this abundance exists only within the observable universe. Beyond it, space continues, structure continues, galaxies continue. And if reality is this crowded within the portion we can see, then the true scale of everything beyond it becomes impossible to ignore. At first glance, the universe seems easy to measure. The Big Bang happened about 13.8 billion years ago, light travels at a fixed speed, and it feels natural to assume that the most distant objects we can see should be about 13.8 billion light-years away. That intuition is wrong. The observable universe does not have a radius of 13.8 billion light-years. It has a radius of about 46.5 billion light-years, giving it a diameter of roughly 93 billion light-years. This is not speculation or exaggeration. It is a measured result, supported by observations of cosmic expansion and the behaviour of ancient light. The reason this feels impossible is that it clashes with how we instinctively think about motion. Nothing can travel faster than light through space. That rule still holds. No galaxy is racing outward at impossible speeds, and no signal is breaking a cosmic speed limit. Instead, the universe grows in a quieter and far stranger way. It stretches space itself. When we say distant galaxies are moving away from us, it is tempting to imagine them flying outward like fragments from an explosion. That image is deeply misleading. On the larger scales, galaxies are not really moving through space at all. They are being carried apart as the space between them expands. A simple analogy helps make this clearer. Imagine dots drawn on the surface of a balloon. As the balloon inflates, every dot moves farther away from every other dot, not because the dots are sliding across the surface, but because the surface itself is stretching. None of the dots sit at the centre, and none of them are special. The universe behaves in much the same way. When a distant galaxy emitted the light we detect today, it was far closer to us than it is now. Over billions of years, while that light was travelling toward Earth, the space between us and the galaxy expanded continuously. By the time the light arrived, the galaxy that emitted it had been carried tens of billions of light-years farther away. This is why we can observe galaxies whose light has been travelling for more than 13 billion years, even though their current distance is more than 46 billion light-years. Light is not crossing a fixed distance. It is moving through a distance that grows while it travels. In effect, light is running on a cosmic treadmill. Early in the universe's history, expansion was slower, and light made steady progress. As time passed, expansion accelerated, stretching distances faster and faster. Some photons manage to reach us because they began their journey early enough. Others never will. This creates a boundary, not a wall, not an edge, a horizon. The cosmic horizon marks the limit of what can ever be observed from our location, given the finite age of the universe and the way space expands. Beyond it, light cannot reach us, not because it runs out of time, but because the space it must cross grows faster than light can traverse it. And this is where the universe becomes deeply unsettling. Space does not end at the cosmic horizon. We know this because the universe looks essentially the same in every direction we observe. The number of galaxies does not thin toward an edge, and the cosmic microwave background, the faint afterglow of the Big Bang, appears nearly uniform across the entire sky. That smoothness would be impossible if space abruptly ended just beyond our view. So the universe extends beyond what we can see. But it does so in a way that permanently hides much of itself. Beyond 46 billion light-years, galaxies still exist. Stars continue to form and die. Black holes continue to merge. Entire cosmic histories unfold in regions that will never influence us and can never be influenced by us. No signal from those regions will ever reach Earth, not because our technology is lacking, but because space-time itself prevents it. Even more unsettling, this boundary is not fixed. As time passes, the observable universe grows, because light from more distant regions has had more time to reach us. The horizon slowly creeps outward. At the same time, cosmic expansion is accelerating, causing space to stretch faster now than it did in the past. These two effects compete. The result is a universe where some objects briefly become observable, only to later slip beyond reach forever. Galaxies we can see today are not guaranteed to remain visible. Their light continues to stretch, shifting into longer wavelengths, becoming thinner and more diluted with time. From our perspective, those galaxies appear frozen at a particular moment in their history. They fade slowly, and eventually they disappear. This is not a distant abstraction. It follows directly from measured expansion rates. If the universe continues behaving as it does now, then in roughly 100 billion years, every galaxy outside our local gravitationally bound group will cross the cosmic horizon. Future observers would see a universe containing only a small cluster of nearby galaxies, surrounded by darkness. They might never know that anything else ever existed. This changes the meaning of observation itself. The observable universe is not the universe. It is the portion of the universe that happens to be observable from where we stand, at this moment in cosmic time. Move to another galaxy, and the observable universe changes. Different regions enter view, while others disappear beyond the horizon. Every location in space defines its own observable bubble. This leads to strange situations. Two galaxies can both be visible from Earth, yet unable to see each other. They may lie on opposite sides of our horizon. Light from both reaches us, but light from one can never reach the other. From their perspectives, Earth itself may lie beyond their cosmic horizon. There is no privileged vantage point, no centre, no place from which the entire universe can be seen. Every observer sits at the centre of their own observable universe. This is why pushing deeper into space matters. By detecting galaxies closer to the cosmic horizon than ever before, observation forces us to confront the limits of what knowledge itself can reach. Those distant galaxies are no longer where their light began. Their later evolution, their mergers, and their final fate are unknowable to us, because that information is still travelling through space, stretched by expansion, and in many cases will never arrive. What we see is not what is, it is what was, and even that view is incomplete. Beyond the observable horizon lies the unobservable universe, regions that may contain galaxies, clusters, and structures just as rich and complex as those we can see. Some models suggest the universe may be infinite. Others suggest it is finite but unimaginably vast. Either way, the observable universe is almost certainly only a fraction of the whole. James Webb has not revealed the edge of the universe. It has revealed that there is no accessible edge at all. And as this realization settles in, another question becomes unavoidable. If expansion hides so much of reality, then something must be driving that expansion to accelerate. To understand that force, we have to confront the most dominant and most mysterious ingredient in the cosmos itself. For most of the 20th century, the story of the universe felt stable. The Big Bang set everything in motion, space expanded, and gravity went to work, slowly trying to slow that expansion down. The great debate was not about whether gravity mattered, but about how the story would end. Would the universe expand forever, or would gravity eventually pull everything back together? Every version of that debate shared the same assumption. Gravity was in control. That assumption did not survive contact with observation. In the late 1990s, astronomers were studying distant stellar explosions known as Type 1a supernova. These explosions shine with nearly identical brightness each time they occur, which makes them reliable cosmic mile markers. Measure how bright a supernova appears, compare it to how bright it should be, and the difference reveals how far away it is. Combine that distance with how fast the host galaxy is receding, and the expansion history of the universe comes into focus. What those measurements revealed was not subtle. The universe was not slowing down. It was speeding up. Distant galaxies were farther away than they should have been if gravity were gradually easing the expansion. The farther astronomers looked, the clearer the pattern became. Expansion had not merely continued, it had been accelerating for billions of years. Something was pushing space apart. To account for this behavior, cosmology was forced to introduce a new ingredient: dark energy. Dark energy does not shine, it does not absorb light, and it does not clump into stars, planets, or galaxies. We do not observe it directly. We infer its existence from its effect on space itself, and that effect dominates the universe. Measurements indicate that dark energy makes up roughly 68% of everything that exists. Ordinary matter, everything familiar, accounts for less than 5%. Dark matter makes up most of the rest. The universe we can see is a small fraction of reality. What makes dark energy especially unsettling is how it behaves as the universe expands. Normal matter thins out as space grows, double the volume of space, and the density of matter drops by half. Radiation thins even faster. Dark energy does not follow this rule. Its density remains constant, even as the universe expands. As space grows larger, the total amount of dark energy increases. This creates a feedback loop. More space produces more dark energy. More dark energy drives faster expansion, and faster expansion creates more space. Over billions of years, this quiet loop shifted the balance of power in the cosmos. Early on, matter dominated, allowing gravity to sculpt galaxies, clusters, and the cosmic web. But as expansion diluted matter, dark energy took over. About 5 billion years ago, it became the dominant influence on cosmic expansion. The James Webb Space Telescope does not detect dark energy directly, but its fingerprints are everywhere Webb looks. In the extreme stretching of ancient light, in the immense size of the observable universe, and in the way distant galaxies recede and fade, the influence of dark energy is written across the sky. Without dark energy, the universe would be far smaller. The cosmic horizon would sit much closer, and vast regions of space we can observe today would never have entered our view. Dark energy does not only shape the present, it determines the future. If dark energy remains constant as current observations suggest, expansion will continue forever. Gravity will still hold galaxy clusters together, but everything beyond them will slowly drift away, crossing the cosmic horizon one by one. trillions of years from now, observers inside a galaxy like the Milky Way would see a universe filled with nearby stars and very little else. The universe would still exist, but it would appear almost empty. This picture, however, is complicated by one of the deepest unresolved problems in modern cosmology, a problem James Webb was expected to ease. Instead, it sharpened it. When astronomers measure how fast the universe is expanding today, they do not get a single answer, they get two. One method looks far into the past, studying the cosmic microwave background, the faint afterglow released when the universe was only about 380,000 years old. From subtle patterns in that radiation, scientists infer an expansion rate of about 67 kilometers per second per megaparsec. The other method looks nearby. Astronomers measure distances to galaxies using Cepheid variable stars and Type Ia supernovae, then compare those distances to how fast the galaxies are receding. This approach consistently produces a higher value, around 73 kilometers per second per megaparsec. Both measurements are precise, both have been repeated, both have been scrutinized. They do not agree. This discrepancy is known as the Hubble tension, and it represents a serious crack in our understanding of the universe. James Webb was expected to resolve it by refining distance measurements. Instead, Webb confirmed the higher expansion rate. The tension did not fade. It became harder to ignore. This leaves cosmology facing uncomfortable possibilities. Either there is an unknown error hiding in the measurements, or our assumptions about the universe are incomplete, or there is new physics we have not yet discovered. One possibility is that dark energy is not truly constant, that its strength changes over cosmic time. Another is that the early universe behaved differently than we assume, imprinting expansion patterns that still echo today. Each possibility carries profound consequences. The expansion rate determines the universe's age, its size, and its ultimate fate. If we are misunderstanding it, then many conclusions drawn over decades may need revision. There's also a more extreme scenario that cannot yet be ruled out. If dark energy grows stronger over time instead of remaining constant, expansion could eventually overwhelm gravity even on smaller scales. Galaxy clusters would be pulled apart. Galaxies would dissolve. In the most extreme cases, even atoms could be torn apart in a distant future, sometimes called the Big Rip. Current evidence does not favour this outcome, but uncertainty remains. What is already clear is that dark energy dominates the cosmos. It stretches space, hides vast regions of reality beyond our reach, and determines what future observers will be able to see and what they will never know existed. It is the reason the observable universe spans 93 billion light-years. It is the reason most of reality will forever remain inaccessible. And yet dark energy alone cannot explain the universe we observe. Because while it pulls space apart on the larger scales, something else must pull matter together on smaller ones. Something must allow galaxies to form instead of dissolving into uniform emptiness. That force is also invisible, equally mysterious, and just as essential. To understand how the universe builds structure even as it expands, we have to turn to the unseen framework that holds everything together. If dark energy governs how the universe expands, then dark matter governs how it holds itself together. Without it, the universe revealed by the James Webb Space Telescope would not exist in any recognizable form. Galaxies would never have assembled, clusters would have dispersed, and large-scale structure would never have emerged. Dark matter does not shine, it does not absorb light, and it does not emit radiation we can directly detect. And yet, it outweighs everything we can see by more than 5 to 1. Roughly 85% of all matter in the universe is dark matter. Every star, every galaxy, every glowing nebula exists inside a framework dominated by something fundamentally invisible. What we see is not the structure itself. It is the illuminated surface of a much deeper architecture. The first hints of dark matter appeared nearly a century ago. Astronomers noticed that galaxies were behaving in ways that defied expectation. Stars in the outer regions of spiral galaxies were orbiting far too fast, moving at speeds that should have flung them into intergalactic space if visible matter were all that existed. They didn't escape. Instead, they remained bound, moving as if each galaxy were embedded in an enormous unseen halo of mass. That unseen mass was dark matter. As observations expanded, the evidence multiplied. Entire galaxy clusters showed the same problem on much larger scales, with individual galaxies moving too quickly to be held together by stars and gas alone. Gravitational lensing revealed distortions in background galaxies that visible matter could not explain, bending light in regions where little or nothing could be seen. Again and again, the conclusion became unavoidable. Most of the universe's matter is invisible. What makes dark matter so important is not only how much of it exists, but how it behaves. Unlike ordinary matter, dark matter does not collide with itself or lose energy by emitting radiation, allowing it to move through space almost without friction. Because of this, dark matter began clumping extraordinarily early. Shortly after the Big Bang, the universe was nearly uniform, with tiny variations in density imprinted during its earliest moments. Dark matter responded first, quietly gathering into growing concentrations while ordinary matter remained hot and resistant to collapse. These concentrations became massive halos, invisible, dominant, and everywhere. As the universe cooled, ordinary matter began falling into these dark matter wells. Gas collected and compressed under gravity. Temperatures rose, nuclear fusion ignited, and the first stars were born. Over time, those stars gathered into galaxies, not randomly, but precisely where dark matter had already shaped the terrain. The visible universe traces an invisible blueprint. This process produced one of the most striking features of reality, the cosmic web. On the largest scales, matter is arranged in vast filaments stretching tens and hundreds of millions of light years, intersecting at dense nodes where galaxy clusters form, and separated by enormous voids where almost nothing exists. This structure is not coincidence. It is gravity at work. James Webb's observations have brought this architecture into sharper focus. By cataloguing hundreds of thousands of galaxies and measuring their distances, astronomers can map how matter is distributed across space and time, revealing patterns that were once only theoretical. The pattern is unmistakable. Galaxies align along filaments, cluster at intersections, and avoid vast empty regions, following an invisible skeleton that shapes everything we see. Webb's ability to see through dust and detect faint, distant galaxies fills in gaps that earlier surveys missed. It shows how early these structures emerged, revealing that filaments were already well established when the universe was only a few billion years old. Matter flows along these filaments, not metaphorically but physically. Gas streams through space like traffic along cosmic highways, feeding galaxies and allowing them to grow. Galaxies do not evolve in isolation. They are connected, supplied, and guided by pathways defined by dark matter itself. Even our own galaxy participates in this process. The Milky Way drifts through space along routes shaped by invisible mass, its motion guided by gravity rather than chance. For decades, the cosmic web existed mainly in simulations, inferred from theory and indirect evidence. Recently that changed. Using gravitational lensing, astronomers detected dark matter directly along the filaments themselves. By measuring subtle distortions in the light of distant background galaxies, they revealed mass where no visible matter could account for it. Dark matter was not confined to clusters alone. It was stretched across space, threading the universe together. This transformed the cosmic web from a theoretical framework into an observed structure. The universe is not a loose collection of galaxies drifting apart. It is an interconnected network shaped and sustained by invisible matter. At the densest nodes of this network lie galaxy clusters, the most massive gravitationally bound objects in existence. These clusters act as anchors, pulling matter along filaments toward their centers and reshaping galaxies as they fall inward. Gas is stripped away, star formation slows or stops, structures are altered. James Webb has captured galaxies caught in the middle of these transformations, revealing how environment shapes cosmic evolution. The cosmic web is not static, it is active, dynamic, and constantly evolving. And yet, despite its influence, dark matter remains one of the greatest mysteries in physics. We still do not know what it's made of, whether it consists of unknown particles or entirely new forms of matter, and despite decades of effort, it has never been directly detected in a laboratory. Still, its presence is undeniable. Remove dark matter from the equations, and the universe we observe cannot exist. Galaxies would never form, structure would never emerge, and the cosmos would remain a nearly uniform fog. James Webb does not solve the dark matter mystery, but it reinforces its central role. By revealing how quickly structure formed in the early universe, Webb shows that visible matter alone could never have done the job. Dark matter provided the head start. It explains why the universe looks the way it does today, the vast emptiness of voids, the dense richness of clusters, and the filaments connecting them like cosmic bridges. Yet this invisible framework operates inside a universe, being pulled apart by dark energy. Dark matter builds structure. Dark energy stretches space. The universe exists in constant tension between these two unseen forces. On smaller scales, gravity wins, allowing galaxies to form and clusters to grow. On the larger scales, expansion prevails, pushing regions of space beyond every horizon. James Webb has shown us that the universe is not merely larger than expected. It is more organized, more interconnected, and more dependent on invisible forces than we ever imagined. What we see, stars, galaxies, and glowing clouds, is only the illuminated surface. Beneath it lies an unseen architecture, and even this vast, interconnected universe is only what we can observe from our position in space and time. Beyond it, the universe continues, shaped by the same invisible forces, unfolding beyond every horizon we can never cross. If you like the video, don't forget to leave a like and subscribe. It makes a huge difference and helps the channel grow.